In this video, we need to cover TCP and UDP in more detail. These are the two transport protocols that carry the vast majority of network traffic. These are layer 4 in the OSI model. They sit between the application layer and the network layer, and their job is to define how data gets delivered. The core trade-off between them is reliability versus speed. TCP guarantees delivery but adds overhead. UDP is faster but offers no guarantees of delivery. Both have a place in IT and OT environments, and knowing which one a given protocol uses helps you understand how it will behave when the network is stressed and what happens when it isn't. TCP stands for Transmission Control Protocol. It's connection-oriented, which means before any data is sent, both sides must complete a handshake to establish a session. You may have heard of this called a three-way handshake. Device A sends a synchronization request to device B. Device B acknowledges it and sends its own synchronization request back. Device A acknowledges that. Only after all three steps completes does the data start flowing. Once that session is open, every packet that device B receives triggers an acknowledgement back to device A. If a packet doesn't arrive, because it was dropped somewhere in the network, device A waits for the acknowledgement, doesn't receive it, and retransmits the missing packet. Data arrives in order and complete. Think of it like certified mail. The sender gets a confirmation of delivery, and if delivery fails, there's a process to handle it. Nothing is left to chance. This reliability comes at a cost: latency. The handshake takes time before data flows. Every acknowledgement adds round-trip time to the data exchange. In most applications, this overhead is small enough to be invisible, but in time-critical control loops, it's worth understanding. TCP is the right choice when data must arrive complete and correct, and when a missed message cannot be tolerated. In OT environments, several common use cases rely on TCP. SCADA polling for register values, where an incorrect or missing reading could cause a bad control decision, uses TCP. Historian data collection uses TCP. Remote access sessions use TCP. Configuration downloads to PLCs use TCP. Any file transfer uses TCP. Modbus TCP, as its name implies, runs over TCP. When your SCADA server sends a Modbus read request to a PLC on port 502, it first establishes a TCP session, sends the request, receives the acknowledgement, and then receives the data. If any part of that sequence fails, TCP handles the recovery. Ethernet IP also uses TCP for explicit messaging, the on-demand request-response style communication used for configuration and diagnostic data. UDP, or the User Datagram Protocol, is connectionless. It sends packets without establishing a session first, and it doesn't wait for acknowledgement. If a packet is lost, it's gone. The sending application never knows, and there's no automatic retransmission. UDP is faster than TCP because it skips the handshake and the acknowledgement overhead. That makes it the right choice where speed matters more than guaranteed delivery. Video streaming, DNS lookups, time synchronization using NTP, and some real-time sensor data can all tolerate UDP data flows. In OT, Ethernet IP uses UDP for implicit messaging, the high-speed cyclic communication where a PLC sends a status update to an HMI dozens of times per second. At that rate, losing one packet doesn't matter much. By the time the retransmit would arrive, there's already a newer reading available. Here's why TCP versus UDP distinction matters practically for OT engineers. If a protocol uses UDP and a packet is dropped, the command or data simply doesn't arrive. No error message, no retry, no alert. For cyclic sensor data being pulled at high frequency, that's okay. The next reading arrives in milliseconds, but for a command that must execute, like a set point change, a trip signal, an open-close command, A dropped UDP packet means the command silently fails to arrive, and the device does nothing with no indication that the command was ever sent. DNP3 is worth specific mention here. DNP3 supports both TCP and UDP. Which one is used depends on how the system was configured. TCP-based DNP3 has the reliability guarantees you'd expect, whereas UDP does not. For critical control applications over unreliable links, TCP is the safer choice, even if it's slower. When you're reviewing the configuration of a communication path in your OT environment, it's worth knowing whether TCP or UDP is in use and whether that matches the reliability requirement of what's being communicated. In the next video, we will cover ports, which work alongside TCP and UDP to direct traffic to the right application on a device.